I'm going to give you 2 lectures about this gravitational interaction. The first one, it's more, let's say, technical. The second, it's for myself, because it's a perturbative approach. I will not be very precise from mathematical point of view, because I'm a physicist, and for me fields and the other ingredients are just functions that transforms in a well-defined manner under some transformations. So I won't use too many mathematical substances. So the lecture is the first lecture is organized on this outline. Namely, initially I shall tell a little few words about the state of the art in the field, in the description of gravitational interactions. Then I shall shortly address the concepts that I use, namely local field theories, gauge transformations, and auxiliary variables. Then I shall do today 2 things, namely I'll address the common second-order formulations of gravitational interaction, namely Hilbert-Einstein and the Lovelock one. And then I shall address the 3 of the first-order formulations, namely Palatini, Hilbert-Palatini, and Arnold-Deser-Mistre. Tomorrow I shall address, as I told you, the perturbative perspective. To start with the state of the art, I shall put here a picture on the left-hand side of the screen with the actual approaches of gravitational interaction. And I shall tell you a story. I read it from a book. I written here, an interesting book, Einstein's Tutor. It's about emulator. In 1914, Einstein, together with Grossman, made some progress in the study of gravitational interaction. And in 1915, he was invited to Göttingen in the field of Klein and Hilbert. At the time, Göttingen was the center of mathematics in the world. Felix Klein condensed there the most famous mathematicians, among others Weil, Hilbert, Noether, and so on. And there Einstein gave 6 lectures of 2 hours about his equations, and Hilbert felt that the equations could be more compactly written and could be more easily studied by using another way, namely the variational principle at that time. So in the fall of 1915, when Einstein presented at the Prussian Academy of Science his discoveries concerning the general relativity, Hilbert presented his own equation, namely the variational principle that leads to Einstein equations. So here in this section, I shall shortly address the ingredients that I'm going to use. Namely, basically, fields in a theory appear as being sections in a bundle, usually a trivial bundle, with the typical fiber, a capital A vector space or associative commutative or ready commutative algebra, and usually the dynamics of the fields are obtained via variational principle, written in terms of a local functional, written here, with the brackets, meaning that meaning here that the function is local. It depends on fields and their space-time derivatives up to a finite order. This is said that calligraphic L, the Lagrangian density, pertains to this space of smooth functions, R-valued or C-valued. Well, for these local functions, we have two results that allow us to offer an infinite Lagrangians that lead to the same equation of motions. Namely, the first lemma is written here for any local function. If the variational derivatives with respect to fields are vanishing, if and only if this local function is reduces to a total divergence. The stronger result is known as the algebraic Poincare lemma. Namely, this holds for local horizontal deforms in this say bundle. Namely, for any form with the horizontal derivative differential vanish, this form is also exact with respect to this horizontal derivation. Among the fields, we have two kinds of fields. Among the sections, we have two kinds of sections, namely the dynamical. It is their equations of motions contains derivatives. Precisely, the equations of motions are surfaces in the jet bundle of a definite degree, strictly greater than 0, and auxiliary fields with that equations of motions are only algebraic relations between fields. It is the equation of motions pertains to the surface in the total space of the bundle associated with the theory. The auxiliary fields are used in physics usually for maintaining covariance on the one side, or on the other side in the context of the PRST formalism, Hamiltonian or anti-field anti-bracket, for constructing the gauge fixed action. For these auxiliary fields, we say that let's say if we have a field theory consisting in two kinds of fields, Z capital A and Y alpha, we say that Y alpha are auxiliary if and only if they get their equations of motions can be solved with respect to Y alpha. It is the relation one holds. This as is it expected, the auxiliary fields do not modify the dynamics of the theory. In fact, we have this lemma that the equations of motions for the theory containing also the auxiliary variables are equivalent with those in which we eliminated the auxiliary variables. By bar S, by this functional, we denoted here the original function, Lagrangian functional, with the Y variables replaced by their solution on these equations. Okay, for a generic field theory, also we have two kinds of symmetries. The first kind of symmetry, it's a rigid one. It could be a discrete one, but we consider here only the symmetries, continuous symmetries. Namely, these symmetries are from the infinitesimal perspective are seen as the transformations of the on the total space of jet bundle, transformations written in this formula, such that their prolongation produce this equation. This is the original expression, let's say, of the Noether theorem. Usually, people takes these transformations only depending on the fields and the point in the space-time manifold. In this formula, by head x, I denoted the prolongation of this vector field on the total space of the bundle to the infinite of the jet bundle. Another kind of symmetry, these are rigid symmetries are also used in the to construct consistent interactions. I remember here the result of Yama in 1966. The theoretical interpretation of interaction, who constructed the known theories at that time, the interacting known theories at that time, like quantum electrodynamics, quantum thermodynamics, even gravity, by gauging the rigid invariances. Okay, concerning the there are another kinds of symmetries in field theories, namely the gauge symmetries. Gauge symmetries that depends instead of real parameters, like in this, like in 5 here. Okay, yeah, epsilon. It's an infinitesimal real number. Replaces the rigid parameters by local ones. Here, epsilon a are functions, real functions depending on the point in the on the base manifold. These are said to be gauge symmetries if invariant also the action. There are two consequences of this kind of symmetries, namely the main consequence of rigid symmetries are the existence of conserved currents, the so-called Noether theorem. Any rigid symmetry leads to a conserved current, and the consequence of gauge symmetries are represented by the fact that the field equations are not independent, namely this Noether identity is false. The conservative charges associated with gauge symmetries are not interesting because they vanish on the covariant space, namely denoted here by sigma. The space of solution of the field equations. What is the consequence of the auxiliary consequences of the auxiliary variables with respect to symmetries, it can be shown that if we have a theory consisting in this kind of fields, Z capital A and Y alpha, with Y alpha an auxiliary field, namely a gauge invariance of S action, namely this Noether identity is 9, lead to a sort of gauge invariances for the action where the auxiliary variables were eliminated. Conversely, it can be shown that if we start from a set of these Noether identities, we can extend these gauge transformations only by adding trivial gauge transformations, either transformations that vanish on the equation of motions. We can construct a gauge transformation for this action, the capital action. So even at the level of the symmetries, even at the level of symmetries, the auxiliary variables do not bring anything new. Okay. The most common auxiliary variables, for example, this are nothing but the momenta, classical momenta, canonical momenta associated with a generalized coordinate for this second order Lagrangian dimension. Let's set the concept of the kth order theory. Namely, we say that the field theory is of kth order if and only if the equations of motions contain at least one kth order space-time derivative. Theta is this surface equation of motions. It's included in the kth order jet bundle and it's not included in k-1 order jet bundle. With this specifications at hand, we shall pass to gravity, to the gravitational interaction, and I shall first address the common formulation, namely the Hilbert-Einstein formulation. In this formulation, the gravitational field has the potentials written here. It constitutes the components of a metric field on a manifold M. It has a non-degenerate symmetric ground tensor. The dynamics comes from the variational principle based on this local functional. Here, the capital lambda is the well-known cosmological constant, and this is the scalar curvature associated with the connection induced by this is this action. It's pertains to a large class of theories, namely those theories that are invariant under the parametrizations. It has this let's say Noether-like equations for ways. But it was in the years 60s and 70s great effervescence between the scientists in South Africa, Lovelock and Loon, who intended to generalize such an action, and Loon proved that in fact in d equals 4, this is the most general action that leads to a second order dynamics, which is invariant under the parameterization. As some exercises that can be done by hand, we can I propose to find this is the main paper. Okay, to find the necessary and sufficient conditions for a theory to be invariant. This is the one-dimensional theory, 1 plus 0 dimensional theories, to be invariant under the parameterization, and also this K-folder theory to be also invariant. There are some simple conditions. For example, one of the conditions consisting in the fact that the Lagrangian here and here do not depend on the time, and also here the Lagrangian function is the homogeneous function in the generalized velocities method, but can be generalized. Well, returning to this theory, if we this is this theory is by excellence a gauge theory. Namely, it is invariant under these infinitesimal gauge transformations written in this formula 13. This can be expressed in terms of covariant derivatives with respect to the Levi-Civita connection associated with this metric chain union. Another exercise, we can by hand show that this gauge transformations are closed only closes of shell. What I forget to say from the perspective of gauge theory, the central object in a gauge theory is the genetic set of gauge transformations. It plays the role of, let's say, the basis of in the for the gauge transformations. If there is any other gauge transformation of a given action, it can be written modulo field equations in terms of that generating set of gauge transformations. This is the generated set of gauge transformations is the main object, the central object in the VRC like methods for quantizing gauge theories. Okay. Following round results, it can be shown that for any, in fact, Lagrangian density for any Lagrangian density that depends on metric and its space-time derivative up to the 2, the field equations are verifies this neuter identities written in Formula 17. Not only the equation, the action that is linear in the scalar curvature, but we can put any function of the scalar curvature, and the field equation associated with that Lagrangian density, it also verify these identities, these Noether identities. To prove this result, one uses only the manner in which the Lagrangian density transforms under general coordinate transformations written here. Okay. The result can be proved easily, namely by using the behavior of the calligraphical under the general coordinate transformations. One obtains these results, these equalities, where we denote it this capital pi being generated from these derivatives of the Lagrangian density with respect to metric and its space-time derivatives. Okay, these are tensor densities of rank of valency 4, 3, and 2, and they are defined in terms of these derivatives via these relations, namely 21. Okay, in terms of these tensor densities, the equations of motion for the general Lagrangian here, okay, takes this expression. Okay, and as we mentioned above, these field equations are of second order if and only if the Lagrangian density is proportional to the Lagrangian. This result of Lund was used by one of his PhD students, namely David Lovelock, to generalize this result in arbitrary space-time derivatives, namely Gauss-Bayon for space-time derivatives. Precisely, Lovelock asked two questions to find an arbitrary space-time dimension, to find the general tensor density that satisfy these identities, these Noether identities. The first, and the second, to identify when this tensor densities of valency 2 comes from a variational principle if this relation holds. In the est, Lovelock asked what is the most general Lagrangian, which depends on metric and its space-time derivatives up to order 2, which leads to equation of motion of second order. The results are obtained in these two papers. Okay, and follows the prescription of the prescriptions of Lund. Namely, he defines these functions. These are not tensors. Only this is a tensor density of valency 6. Okay. And define via the same rules of Lund these tensor densities in formula 28. These are obtained as in formula. These are given by formulas for formula 21 by replacing their 21, replacing their capital lambda with with lambda mu. Okay, using only the transformation law of this tensor densities of valency 2 under the general coordinate transformations, log find that the quantities written here should verify these equations, namely, these relations. Okay, and the Noether-like identities imposed are equivalent with these purely algebraic relations among the derivatives of the tensor densities with respect with the second order derivatives of the metric. These relations written here are equivalent with these equations. Okay, due to the fact that these tensor densities are symmetric in each pair of indices mu, alpha, beta, lambda, rho, and this integrability condition should take place. Okay, it results that the tensor densities written here are completely symmetric in the space in the pairs mu, alpha, beta, and lambda. Okay, using this tensor densities of valency 6 and the previous tensor densities of valency 2 written in Rund approach, we defines the family of tensor densities written in this formula by derivating repeatedly these tensor densities with respect with the second order derivatives of the metric. Due to the fact that this depends only on the metric and its space-time derivatives up to order 2, it results that this family consists only in tensor densities of various valencies. Using an inductive argument, it can be shown that these tensor densities enjoy the properties, namely they are symmetric in each pair, pair of indices here, 1, 2, 3, 4. Okay, are symmetric under the permutation of the first group of indices and any other pairs of indices. Okay, and cyclic identity between the first index here and any two indices in pairs, namely an identity of the type of this type. Okay, with this result at hand, log proved that the tensor densities in the family above are vanishing whenever at least 3 of their indices coincide. This implies that the family of tensor densities contains at most entire p plus 1 over 2 elements. By integrating these definitions, these relations from the top to the bottom, we can express finally the the original, the starting tensor density, mu, under this form with ck bar here arbitrary real constants. And the tensor densities written here being nothing, being functions only on the metric. Okay. It is immediately to see that for space-time dimension, for space-time dimensions, this integer has the value equals to 2, and this sum reduces to two terms, namely the cosmological term and the standard term, that proportional with the scalar curvature. Okay. Here I told you that this depends only on the metric. This coefficient depends. This tensor densities depends only on the metric, and also Lovelock proved that they are proportional in fact with the inverse of metric and with this delta like products, anti-symmetrized delta products. So the most general tensor density of valency 2, which satisfy the Noether identity, the Einstein-like Noether identity. It's better written in formula 34. Okay, and its equation. Okay, the second to answer to the second question, namely to find the Lagrangian density such that these tensor densities of valency 2 are nothing but the equation of motion for corresponding to that density. It results that this Lagrangian density takes this form. So for any so in space-time dimensions greater than 4, there exist Lagrangian densities, which are depending on the metric and its second and its first and second space-time derivatives, which produces second-order field equations. Of course, as I already mentioned, this Lagrangian is not unique. By adding total divergences, we do not leave the original field equations. We shall see also that in the perturbative approach of the gravity, that this Lagrangian density can also be addressed. Well, next I shall discuss the standard first-order formulations of general relativity, and I'll address those formulations that are suitable for generalization. I do not address the first-order formulations pictured at the beginning of the talk, namely HTK and CDG and so on, because I want to address those first-order formulations that are suitable for any space-time dimension, greater or equals to 4. The first formulation, the so-called Palatini formulation, comes from the Hilbert-Einstein action, and interpret the linear coefficient, the linear connection coefficients as independent variables of the metric. This can be done because the gauge transformations of the metric and associated gauge transformation for the linear connection coefficients can be written only in terms of on the metric and these coefficients. So in Palatini formulation, the field spectrum consists in this kind of these fields with this arbitrary fields only subject to the symmetry in the lower indices, and here this is symmetric in upper indices, and also this determinant is non-vanishing. With this specification, the Palatini action is written in this formula. Here, J mu, the metric is interpreted as a rational function of the J hat fields. A rational function, namely the unique solution to these algebraic equations, purely algebraic equations. The action P5 is found to be, by construction, to this gauge invariance. Okay, and this is consistent because here the covariant derivatives can be written only in terms of these fields, let's say. In this Lagrangian action, both fields J hat or gamma can be complementary regarded as being auxiliary. Precisely, we can eliminate or gamma on its own field equations of motion, or J hat on its own equation of motions. Namely, for example, if we eliminate gamma on their equations of motion, this means to solve these equations here. These are solved successively by contracting with delta, and then to get to this relation, we allow to express this. And the solution of this equation, namely the solution of the elimination of the fields capital gamma, are nothing written here, and the bar action obtained by the elimination of gamma is written here, is nothing but a Hilbert-Einstein action written in terms of the second rank to tensor J mu. As I told, in the same action, we can eliminate not J hat but J alpha beta. Here the coefficients of metric are regarded as being rational functions of J alpha beta. Now we can write the Lagrangian density only in terms of the linear connection coefficients gamma as in formula written here. This Lagrangian has been written, constructed first by Schrödinger. The second first order formulation, which is used mainly when the gravity is coupled with spinor fields, is the so-called Palatini formulation. Here, the fields of the theory are these field-bind fields and these fields with which are symmetric in the Latin indices. The field-bind here are related. The field-binds here are related with the metric formulation by this relation. Here by eta AB is nothing but a flat metric written in this this formula. In the round language, EA and omega AB are some one forms on the space-time manifold. With the help of this one force, we introduce these two forms known as torsion and aperture. And we see that from this relation that connects metric in the metric formulation and the fields A and nu, but this relation is invariant under this transformation, where here phi AB are some functions, small functions defined on M with SO1 minus 1 value, namely the matrices that invariance is the mismatch. With the help of this relation, by asking for TA for the to transform in the same manner as the field-bind fields, we get the transformation flow for this one forms as in formula H. Also, this transformation law, together with the second definition here, shows that the curvature transforms under this to these transformations HP3 and HP4 as in this manner HP5. Putting all together with this let's say invariance of the Levich beta, d-dimensional Levich beta tensor to the SO1 d-1 transformations, we obtain this deform HP6 formula, which is here is first one, which is manifestly which is invariant by construction to these transformations HP3 and HP4. Here by phi is an arbitrary function written here. Okay. At the same time, this the form contains only geometric objects, so that its the derivatives with respect to any field satisfies to any vector field that satisfies these relations. This is due to the Cartan rules of the derivatives. And translating this into the language of gauge fields and gauge transformations, it results that this the form or it's invariant under these gravitational transformations, with here theta A B arbitrary functions, SO1 dimensional functions, and epsilon rho arbitrary smooth functions. This reveals this by integrating the previous deform, we obtain this Lagrangian action written in this formula, the so-called Hilbert-Palatini Lagrangian density. In this formula, we use this equations, and let's say these are algebraically, purely algebraically related by this these fields, and by E we denoted the determinant of also here E A mu and omega plays complementary roles. It can it can be interpreted as auxiliary variables, namely by, for example, by eliminating the fine spin connection coefficients on their own equations of motions. We get these relations, and this can be solved with respect with the fine spin connection coefficient. By passing to these new fields, and the equation of motions can be brought to this relation, which solve this contraction written here, and finally express the fine spin connection coefficients as in this formula. It is it can be shown that this, in fact, these relations can be obtained simply by imposing the torsion, the vanishing of the torsion as in this formula. Okay, by replacing these solutions into the Hilbert-Palatini action, one gets nothing but this action, with which is nothing but the Hilbert-Einstein functional, which depends on a metric expressed in terms of this field-binding field. Contrary to, in addition to the original Hilbert-Einstein equation, this action is invariant under these additional gauge transformations that remains also after the elimination of auxiliary variables, which means that to reach the Hilbert-Einstein formulation, we should impose a partial gauge fixing condition on the field-bound fields, namely this condition is usually the non-canonical gauge fixing condition. Okay. The third first-order formulation, it's the let's say the Hamiltonian version of the Hilbert-Einstein formulation. And was done first by Arnovitz and Meissner, so-called Adena formulation. In this formulation, one uses the slicing of the space-time manifold into space surfaces, and it realizes foliation of space-time manifold in terms of space like surfaces that are parameterized in terms of the time parameter, and uses this embedding of the space-like surfaces, space-like hypersurfaces in the space-time manifold. To do this, I collect some things, some elementary things from the Riemannian geometry, namely if I have a Riemannian manifold here, sorry. Okay, and submanifold, an embedded submanifold. I can put on this submanifold an induced metric via the pullback map, this dimension, with this the connection between the metric on n and the metric on sigma written in this relation. Okay, the induced metric is also non-degenerate, and with inverse written in this equations, due to the fact that the submanifold is embedded into the space-time, into the manifold, mother manifold M, say. Okay, these tangent vector fields can be supplemented with some normal vector fields in the matter manifold, satisfying this relation. So the geometry of the matter manifold can be transferred to the embedded surface sigma. Okay, and the connections between two geometries are first written here, and these connections or these relations involves these coefficients written in formula A3 with where I use these notations, coefficients that transfers the geometric objects from mother manifold to the surface. Here A, B, C, D are some local functions, are local smooth functions on M. Based on these ingredients, we introduced the extrinsic curvature. We first enjoyed this. Okay. Also, using the expression of tangent vectors, local tangent vectors, we have this relation. And we can express the coefficients written here in these formulas that connects the two geometries as being written in formula A5, and by using the significance of these objects, okay, one can deduce various identities between quantities A, B, C, D, local smooth functions. Okay, these are used, as I told, to connect the two geometries from the mother manifold to the one, namely to connect the Riemann tensor on the mother manifold to the Riemann tensor on the embedded submanifold written in A9, and also relation A13. For our embedding, for our situation, our model manifold is a signature 1 d minus 1, and the surface is the space-like surface written here, with the original parametrization. We have these identities, and we have only one normal field written here. So in this normal field, the inverse of the metric is written in A515, and the components of the normal vector field enjoys this, which allows the expression of the metric and the inverse of the metric in this formula. With n written here are the lapse and shift function. This decomposition is used to express Lagrangian suitably to such that the Dirac formalism implements directly the associated constraints. In this setting, namely the R of d minus 1 hypersurface, we have the extrinsic curvature written here, this coefficients vanishing, and also the relation between this extrinsic curvature and the induced metric on the hypersurface space, like hypersurface, and the covariant derivatives on the normal vector fields, lapse and shift. Also here we have these relations between the spatial part of the Riemann tensor on the model manifold and the Riemann tensor on the embedded surface, hypersurface, and with this relation, the original Hilbert-Einstein Lagrangian can be written up to a total divergence, as in formula A18. With calligraphic R and gamma, the objects associated with the embedded hypersurface, and kappa, the extrinsic curvature. Okay, these are defined usually by this formula. In this decomposition of the Hilbert-Einstein Lagrangian, the current F mu has this concrete expression. So at this level, the Hilbert-Einstein Lagrangian, this is here. Depends on lapse and shift, and the induced metric on the space-like hypersurface, and is written in this formula. At this stage, the Dirac formalism follows as usually, namely from the definitions of canonical momenta associated with the lapse and shift, we get these primary constraints. Okay, and from the definitions of the canonical momenta associated with the induced metric coefficients. We can express its time derivatives, express the generalized velocities as in this formula, and we can complete the canonical Hamiltonian by performing this Legendre transformation. This is, of course, well defined only on the primary constraints surface. The canonical Hamiltonian is written in this formula A23. So at this point, the phase-space variables are the momenta associated with the Lagrange shift, and also the canonical momenta associated with the induced metric coefficients. This means that the canonical structure written in the Witt condensation is written in A26. At this stage, one imposes, as usually, the consistency of the first class of the primary constraints, namely to the condition to be preserved in time. This condition, together with these Poisson brackets, exhibits the constraints are written here. Okay, secondary constraints. By direct computation using Poisson brackets in the functional, computing the Poisson brackets in the functional sense, so we can prove that these secondary constraints verify these relations A26. So at this stage, the Dirac formalism stops. We have the gravitational field possesses 8 constraints, all of first class, and the quantum approach requires, of course, some gauge condition and solving this, passing to the reduced space and identifying the fundamental object. But this is only speaking because due to the higher nonlinearities in the secondary constraints, and also maybe in the gauge fixing conditions, this cannot be done. This is all for today.